Well, good morning, everyone, and welcome to our inaugural Professor Meyer H. Birnboim Lecture Series. The series that we're starting today honors the life and work of Meyer Birnboim, who was really a professor of mechanical engineering here at Rensselaer for about 30 years. Right? So you might wonder, well, why is chemical and biological engineering hosting this inaugural lecture? And there are several reasons for it. Meyer's work focused on using optical techniques to measure the rheological and also the optical properties of materials. And of course, rheology is a core area of chemical engineering. Shortly after Meyer joined Rensselaer, the school reorganized into a grid system, which sort of looked like the way our National Science Foundation is organized. And what that meant was all the thermal fluid folks, which was like the majority of people in mechanical engineering, joined most of the people in chemical engineering in an organization that turned out to be run by Louis Coonley, who was a former chair of our department. The grid system really didn't last very long. There was a lot of internal tension involved with it. But the legacy of promoting collaborations between disciplines still survives to this day at the Institute. It's easy for us to do that. But lastly, I was one of the last people to collaborate with Meyer back when I was an assistant professor. He was actually the first person outside of chemical engineering with whom I worked. And what was even more flattering was he came and actually approached me about collaborating with him. He had sort of learned that I had made these polychromatic glasses when I was working at Corning, and he had developed a theory that described all of their optical properties. So it was a sort of nice and, we're going to say, natural collaboration for us to start. Meyer was truly one of the kindest and most generous people I met at Rensselaer. When our new president came and asked us, what do you like most about Rensselaer? It wasn't sort of the location, and it wasn't the size of the school or anything like that. It was the people, and Meyer really exemplified, how nice and inclusive people are here. Turns out he's also the first person I had ever met from Winnipeg, which was kind of neat in and of itself. The Professor Meyer H. Birnboim Lecture Series is a joint series between chemical and biological engineering and physics, applied physics, and astronomy. The event's going to alternate yearly between the two departments and between the two schools, really thanks to efforts from our deans, Shekhar Garde, Dean of Engineering, and Kurt Brenneman, the Dean of Science. The series topics are also going to alternate, with rheology being the primary topic on the engineering side and optics on the science side. Thus, the series serves a similar purpose to the event we held last week, Our Life at the Interface of Science and Engineering, trying to promote collaborations between scientists and engineers. I'd like to especially thank the Birnboim family who are here today for their idea to found this lecture series, and of course for their generous financial support of the series as well. We're really happy to have them here with us today to help kick off the series and celebrate the life of a special person. So before we introduce today's distinguished speaker, I'd like to yield the floor to Meyer's brother, Chaim Birnboim, who will talk a little bit about the genesis of the series and what Meyer meant to the entire Birnboim family.
Thank you very much. I guess the microphone's working. I'm Chaim Birnboim, one of two brothers, one of Meyer's surviving two brothers. Seeing if this works. It does. So about a year ago, which was 25 years after Meyer Birnboim, Harold Birnboim passed. We, his two younger brothers, Roy and I, his wife, who's here, one of his two children are here. Both his children gathered together, thought how this time has passed and how we could properly honor his memory. Now, in addition to his being a much beloved husband, father, grandfather, and brother, Meyer's chosen career was science and technology. At different points in his career, he was, as we heard, we were from Winnipeg, Manitoba, Canada, and for Americans, it's kind of north of Minneapolis, roughly. He obtained a master's degree in physics after he left Winnipeg at the University of British Columbia, and then a PhD in physics at the University of Wisconsin under the supervision of someone I'm told is a giant in the field, John D. Ferry. He was also a visiting scientist at the Carnegie Mellon Institute in the lab of Guy Berry, and he was also subsequently at different times, visiting scientist at the Weizmann Institute in Israel in the lab of Max Silberberg. But his home institution was this one. It was the Rensselaer Polytechnical Institute, where he was a professor in, I think the names have changed, but mechanical engineering and physics for nearly a 30-year period. My own background is in life sciences, so it was from my dear brother Meyer that I learned the meanings of the words rheology, viscoelasticity, and quasi-elastic light scattering, where he carried out his pioneering work. However, I never did get to see the Birnboim-Schrag multiple lumped resonator that bears his name. As a family, we decided that the most appropriate way to honor brother and father and husband Meyer was to choose an endowed series in his names here at RPI. Then direction was given to choose speakers whose research interests reflected the different areas in which he worked, made significant contributions, and as we heard, they'll alternate between Department of Chemical Engineering and the Department of Physics. And I was very pleased this morning that we had chosen Dr. Wagner, who I didn't know, but I read his most impressive resume, and we met him this morning, and it was wonderful to hear, and he seemed like such a perfect candidate for this series. Now, it's my understanding also, as Joel Pawlowski mentioned, he's still the only person on staff who's had the continuity, remember that? And we thank him and Professor Shekhar Gard, the Dean of the Faculty of Engineering, and Drew Babitz, who helped organize this year's lecture and make it a reality. So it is our hope that future generations of the Birnboim family, some of whom may attend this school, but will attend this lecture in future years, and take pride in the accomplishments of one of their ancestors. We have today with me, his brother, my son Elliot, his nephew from Toronto, and Meyer's son Yossi, who lives in New Jersey, and his widow who lives, Alma, who lives in New York. My other brother, surviving brother, Roy, unfortunately could not attend for medical problems. Thank you very much.
Thank you very much. So I'm very pleased to. You're fine. Okay.
I don't know why it went to sleep. I apologize. Here we go. You want the title slide?
Okay. All right. Great. So I'm very pleased to introduce Professor Wagner here. So Professor Wagner is an assistant professor of the University of Delaware and holds a distinguished Unidel Robert L. Pigford Chair in Chemical Engineering with affiliated faculty appointment in physics and astronomy, biomechanics and movement science, and biomedical engineering. Wrong list. And not only that, he was the president of the Society of Rheology and is also co-founder and the director of the Center for Neutron Science at the University of Delaware. So then he also served as the chair of the CB department from the 2007 and 2022, and he also holds the membership of the National Academy of Inventors and National Academy of Engineering. I think there is only one more, the National Academy, the position that I believe the Professor Wagner will obtain soon. And he is also a fellow of both the AAAS, American Association for the Advancement of Science, and NSSA, Neutron Scattering Society of America. So in 2018, he was awarded the Sustained Research Award of the Neutron Scattering Society of America, too. It's great. So Professor Wagner is also co-founded STF Technology LLC and to commercialize his inventions for the application in personal protective equipment and astronaut protection for NASA, as well as new scientific instrument. So please join me welcoming Professor Wagner for the inaugural lecture series.
Thank you, Ted. Thank you very much. Well, it's quite an honor to be back here, and I really want to thank the family, the Birnboim family. Thank you for the wonderful introduction. It's in our conversation this morning with you and Alma and the rest of the family. We learned a little bit that we had actually overlapped or had similar mentors, if you will, at Carnegie, what at the time was Mellon Institute of Technology and Carnegie Tech. And as I'll try to show you today, there's connections that run deep. Rheology is a small community. And hopefully my physics background will count also for some of you who are looking for a physics lecture. We're going to talk about neutrons, right? Okay. So long title, a lot of people from my company, from different NASA centers, and also CMORS, which is on our co-located on our campus, and funding from different agencies. So let's get into it by starting just a few slides about some connections. So there was perhaps the most highly cited piece of work of Professor Birnboim has to do with calculations, theoretical calculations of the optical properties of nanoparticle or particle systems where you have core shell structures. There are many other contributions in nanocomposites in that deal with rheology as well as optical properties. I highlight this one in particular, the quote here. The surface-mediated surface plasmon resonance conditions are presented for these model nanocomposites, and shown over here is a graph that shows an enormous enhancement. The scale is logarithmic, 6-7 orders of magnitude of a surface plasmon. Now, I'm not going to go into the details of surface plasmons, but trust me, they're really cool. And if you have a surface plasmon, 2 years later, we were working with a group in Germany at Mainz, doing essentially the same, but experimental side of it, using the theory. And the concept was we could use the concept of the core shell calculations to look at particles, in this case gold nanoparticles, which are very optically active. They have beautiful ruby red color at that size in the nano range. And we were absorbing biopolymers to the surface and measuring the absorption characteristics and the kinetics, which was made possible because of the theoretical work that was there to tell us how to interpret the optical signal. So when you have a nanoparticle, you cannot see it, right? You cannot see a single polymer or nanoparticle in solution. You can put them in an SEM, but it's virtually impossible to see them in any way. So this was an interesting experiment. This was done not only with the Germans, but with actually Kodak, because we were working on photographic film and X-ray film and trying to improve the clarity and the ability to detect cancer and things earlier on from the film pictures that people would take from X-ray. So that's one example that I'm very proud of, that there's a nice connection there. The next example is going back to the rheology, and this was, I found really fascinating and is the basis of a lot of fun. By the way, that other technology is used heavily. The idea of using nanoparticles and the surface plasmon resonance to look at absorption is used in diagnostics, and that was 20 years ago, and now it's a a well-used technology in the field of biochemistry and biophysics. There's a beautiful piece of work here with an equation that we all know, right, from fluid mechanics. Those of us who study fluid mechanics, the relationship between the viscosity and the particle size for a Brownian particle moving around in a fluid. And this was exploited to look at high pressure. When you deal with really high pressure systems, it's virtually impossible to measure their properties because you've got to put them under this high pressure. And any time you want to interrogate them, you've got to go in with a rheometer tooling or something. You cannot do it. So the cleverness here was working with Hans Wies in mechanical, and what they did is they took the high pressure cell and they used sapphire windows and they put a laser through and they measured the diffusion so that they could get from the diffusion coefficient the particle size, and then they could get the viscosity back out. And so they could measure viscosity, and there's data and theory for water. And our interest now, 20-some years later, is on more viscoelasticity systems, right? Polymers and that. And so this slide with lots of things on it, if you think about food, if you think about biopharmaceuticals or flu vaccines, if you think about shale gas extraction, you're working at potentially high pressures. People use pressure to kill off bacteria and to prepare food without heating it up, which destroys its properties. But that high pressure, it's difficult to understand what's going on. So we're using neutrons to look at the structure instead of light, and then simultaneously using the light scattering, but now in a slightly different form, multiple scattering called DWS, but the same basic principle, to measure the viscoelasticity of the fluid as well as the structure under high pressure. It has a nice acronym HP Micro Rheosans. It's work done by a graduate student, Brian Paul, working with the characters on the right there. Some of you may know Eric First being an expert in diffusing wave spectroscopy, my good colleague and neighbor, Braimy Lenoff, on the proteins that we're working on, Susanna Texera, who's the mentor at NIST, who's an expert on food at high pressure with neutrons. Okay, so that's the two connections. There's more, the resonator and other rheology, but I'm going to stop with that so I get to talk a little bit about my work. So two topics. I want to start off with some basic science and physics of neutrons and rheology, and then I want to move to how we're using it to explore space. Okay. So just briefly, University of Delaware is in Newark, Delaware, just south of Philadelphia, just north of Baltimore, but we're close to Washington, and near Washington is the Center for High Resolution Neutron Scattering. This is big science. You need a nuclear reactor, gigantic experiments, right, that require lots of people, and it's a fantastic opportunity for us to be a short distance away and use the facility. Now, I wear many hats, as you heard in the introduction, but for the next slide, I'm a chemist. And it's a short video prepared by the American Chemical Society. It's a little dated, but not too dated, about the kinds of things we do. And I think it does a nice job of introducing the technology to you. So I'm going to play this, and it just takes about 2 minutes. Chemists are good at inventing things. We create things. We're molecular engineers, if you will. So by nature, chemistry enables us to make things that are useful for society. We translate molecules into ideas and products that could be useful for people. I'm Norman Wagner. I'm a professor at the University of Delaware in the Chemical and Biomolecular Engineering Department, and our company's called STF Technologies. I'm very proud of the team that we've assembled. It's a very interdisciplinary group. A number of years ago, we were working on these shear thickening fluids. Shear thickening fluids are very unique materials because they're field responsive fluids. The harder you push, the more it pushes back. That kind of response, which is not the normal response, can be harnessed in a creative way. We're trying to really provide protection where it doesn't exist. They might benefit first responders, police, military. One of our products that we're working on right now is with NASA to protect astronauts. And you'll see Rich and Eric and Maria and others trying to formulate special chemical formulations that will withstand the rigors of space, especially when we start talking about living and working on Mars. Some of the early work we did in ballistics and puncture resistance for body armor translates over to things like puncture-resistant medical gloves for use by surgeons.
I have an ice pick here. If you stab the conventional Kevlar, you can see you very easily go through. I use the shear thickening fluid treated Kevlar. You can't get through.
Our partnership with the Army Research Lab is really essential to enable us to translate and take our ideas out of the laboratory and bring them into the real world practice.
We had this idea that if we could get the response of a shear thickening fluid, but in something that's more like a strap that is speed dependent in its response, you could potentially make some sort of supporting wearable devices that could prevent concussions and head injury. Working with chemists is great and it's really important. You really need a chemist in there to do the details of how do I get this material to be compatible with that material. From there, once you have a technology that's new and different, it can do something that no other material can do, then just applications will come to you, things you can't anticipate.
And when you talk about prosthetic devices, the ability to provide people with a more realistic, lifelike prosthetic device is really critical to balance out the gait.
To be able to use the fluid to dampen the forces to a limb would be pretty remarkable.
To try to match the range of motion and the kinds of forces that the patient would feel.
Basically, we're trying to use the shear thickening fluid tethers to customize it to each specific patient, each specific person. So that way they don't have to switch out, oh, I'm going to go running today, I need to use a different prosthetics. It's definitely a team collaboration, and I'm happy to have a team.
Our business is inherently interdisciplinary. We need talents and skills that go beyond any one particular discipline. Chemistry is at the heart of it, but there's so many other science and other soft skills that have to come together to be successful. And that playground is vast, and the opportunities are enormous to be able to do this.
So this was made by the American Chemical Society, and they showed it at South by Southwest, the music festival in Austin, and the idea was to get entrepreneurs and people interested in working with chemists. Kind of worked. Okay. So what are these shear thickening fluids? I once got a call in my office from some guys from a show called Mythbusters, and they wanted to put people wrapped in my body armor in the San Francisco Bay and have them attacked by a shark. And I was like, nah, I don't think that's what I want to do. But they ended up doing the oobleck. And I think many of you who have children have played with oobleck, right? Dr. Zeus and that. It's the cornstarch and water. And you see you can walk on water if you move quickly, you go slowly. All right, so some science for a while. So we've got ceramic nanoparticles, not cornstarch and water. We put the nanoparticles into a carrier fluid, and we have the property of viscosity we're all familiar with, right? As a function of shear rate or shear stress, and it's Newtonian. And you add more particles, and you get shear thinning, and eventually you get this shear thickening, where the viscosity goes back up again. But this is a log-log plot, and we're humans. We don't interact on a log scale with things, right? We touch stuff, we feel stuff, it's linear. So if you put it on a linear scale, this is what it looks like, right? So essentially, it's very low viscosity material, very low stress until you hit a certain critical shear rate, and then bang, it goes off scale, right? And we'll learn a little bit more about why that happens. So at rest, the fluid, you could tip it. It's 70–80% ceramic, a liquid, clear. The optical properties in this case are clear because of the match of refractive index. You can use the theories of Meyer Birnboim to prove that. But at high stresses in the shear thickened state, it's a solid material. And so you see here that you could stir it a little bit and pick up the jar because it's under force. So that type of material, and that's reversible. If you take the stress away, it goes right back. We spent quite a bit of my early career working to prevent shear thickening. Whether you're trying to build, in case the Freedom Tower, or in France, some of the key highway bridges, or the Tapazy Bridge here, this technology wasn't possible. The concrete cement technology wasn't possible until they figured out how to prevent shear thickening, so they get the particle loading they needed to get the strength they needed to build the kind of structures the architects wanted to build. Toothpaste, X-ray film, paper coating, painting. You don't want your paintbrush to stop moving because it shear thickens, right? So you've got to figure out how to stop it. Then we started thinking about ways to use it in a productive way. That started with the body armor work, for which was awarded an award by the US Army for that. And then we moved to other technologies because people came to us. One I'm very proud of is women's sports apparel. Reebok, it's one of their best product launches ever. Time Popular Science had as one of the better inventions of the year. And then, of course, I'm going to show you today our work with NASA and how we use it, the shear thickening response to help us. But we need to understand a little bit where it comes from, how to control it. And this is the science part of the physics part of the talk, if you will. We all kind of know if you have a particle in a fluid, the fluid has to go around it. That's sort of a hydrodynamic effect. And if I have more particles in a fluid, that hydrodynamic effect could be very important. I came up here from Delaware on the train, of course, the Amtrak. The Amtrak, you think about how a wheel works, whether it's your car, a bicycle, a skateboard, a train, right? You've got bearings, and this was worked out by Reynolds, right? Steam engines, we had to get power, right? We had to have shafts, we had to have bearings to support the transfer of power. And one of the earliest engineers, true engineers, Reynolds, Osborne Reynolds, in the 1800s, worked out all the fluid mechanics and rheology of this problem. And so as you have a bearing and these ball bearings move around, they never touch, right, because of the grease, the oil that's in there. It's critically important, generates very large stresses. Fast forward 100 years, go to Cambridge, and George Batchelor's venerable fluid mechanics group that was working on understanding this in some great detail. And he did the calculation for two particles in a flow field, and what they found was that the stress required to squeeze the fluid out between those two particles, so-called lubrication force, goes to infinity mathematically for perfect spheres, for perfect particles with a Newtonian fluid. And it also leads to an interesting phenomena of closed streamlines, such that if two particles get close together, because that force becomes so large, they will stay together and orbit together. And this was known in the 70s. But we started thinking about, well, the force needed to move the fluid really increases when these hydrodynamic interactions increase. But it could be some kind of a feedback when you have more particles in the system. So at equilibrium, if we have a suspension of particles, cartoon shown here, just moving around by Brownian motion because they're nanoparticles or colloids, I put them under flow, they tend to organize themselves. You could think of the analogy of traffic, right? At equilibrium, it's sort of like a parking lot, cars go in, they move, but you got to kind of dodge the other cars, things are moving randomly. Once you get on the highway, you can move much faster, even at high densities, because everybody sort of follows each other. But if you have a disruption, and I like to go to India, I have relatives there and visit, and this is, right, what happens, right? And you get a traffic jam, it locks up, right? So if particles begin to associate and form these large clusters, due to this hydrodynamic effect, they can shear thicken. And this was the basis of the science with that we're going to talk about. And so we have these cartoons you'll see again and again. Equilibrium, shear thinning, shear thickening, different states. It's reversible. You can go forward and back. So what evidence do we have? Well, we spent a long time, and I won't dwell on this slide. You could think, well, okay, if that's true, then I could change the fluid. I could change the particle size. I can change the polydispersity of the particles. I could change the shape of the particles. I can put charge on the particles. I can change the hardness of the particles. I can coat the particles, and we'll talk about this a little bit more, but there's a lot you can do to control that shear thickening and make better concrete, big new buildings like the Freedom Tower, okay? There's another theory, and I throw this gratuitous cartoon up there that recently appeared in Advances in Engineering on some of our work. I do a lot of work with NASA. Sand. So when you go to the surface of the moon, the sand pile, it's because of friction. Sand particles touch each other. They don't have fluid in between them, right? So there's contact friction. So what if the particles de-wet and touch and then act more like sand? Even though they're in the fluid, what if they actually touch, right? Well, we know what happens. 1600s, Hamilton's law, right? So, the force diagram. What is the friction on a block sliding down every, high school student's physics problem, right? It depends on the normal force, right? So that if you have a normal force, particles push together, they don't want to slide, right, against each other due to the friction. So what controls it in our system? Is it this frictional force? Is it the fluid mechanics force? Let's see what evidence there is. Well, luckily we have lots of people doing theory who collaborate with us. And so the initial work was done with George Bossis and John Brady, and I'll tell you about that, where we used Batchelor's work, but they've coded it into a computer so you could do the many-body hydrodynamics problems. We're going to talk about Jeff Morris's work, where they put in contact friction. Then we're going to look at particles that have a bit of an elastic surface. This turns out to be important if the particles are a little soft. Or particles that might be rough but don't actually touch. Okay? So those are the prevailing theories. So let's take a look. I need to get very technical for a moment in rheology, but if you don't understand the rheological thing, it does not matter because the physics is visualized here on the right. I think we all know what viscosity is, resistance to flow. But when you look at rheological properties, there are two other properties that are important in a shear flow. They're called normal stress differences. They're like pressures. And the simple way to think about it is, on the right here, if I have a normal stress that's positive, if I extrude a polymer, it swells. And this is what makes polymer dyes so expensive to make, because you size them, you push the polymer through, and it comes out a different size, right, because of this dye swell. That's a positive normal stress. If I have a Newtonian fluid, has no normal stress, it comes out the same size. And many large particle suspensions have a negative N1, so they actually come out smaller, right? They contract. Now, that shear thickening effect has some interesting phenomena. You have to be a little careful, so I'm going to distinguish against dilatancy. Those of you who've gone to the beach and maybe run along the surf zone, you see how sand gets kind of white where your foot steps on it. It actually gets dry, right? Because the sand dilates and there's not enough water to wet it. And it turns out Heinrich Jaeger at Chicago took our data and data from many other labs and plotted it up as the maximum stress that you could get in the shear thickened state. Here's an example from BASF on a paint formulation. You can see it horribly shear thickens, but you get this maximum point here you can't go above. That's one of the points on this graph of that maximum stress, plotted against the surface tension and the particle size. So that's the capillary force holding the particles in the liquid. So if you push these systems too hard, they want to escape. The particles want to get out of the liquid. They want to dilate and expand. We're not going to talk about dilating systems today, so we'll stay below that maximum stress. So I need to go through this data set just for a second. So it's a model system of the particles I showed you before, the nanoparticles. And what the student did here very carefully was measure the viscosity at different particle loadings. And you can see the beautiful shear thickening effect. Those curves are forward and back, by the way. That's perfectly reversible. Then he measured this first normal force. And it's negative, so we put a negative sign there. And you can see in the shear thickened state, when you get to those high shear rates, it goes up a lot. And it depends on the particle concentration. And the second normal force. No one had actually measured these things before, carefully, right? There was bits and pieces of information, but we did this and we generated this nice data set, which then spawned a whole industry of people with theory and simulation trying to see if they could match it. So the point I want you to remember is that normal force is negative, it contracts, okay? If you put it through a die, and this is that liquid ceramic. So John Brady and George Bossis did some beautiful simulations on these systems, and we put that up against our data, and lo and behold, you can see for a particular concentration that they simulated, which is close to between the blue and the pink, it's got a mild shear thickening, and that's using the perfect hard spheres with the Newtonian fluid. The effect isn't there. Jeff Morris, Morten, and others looked at this problem, and they said, well, what if the particles do touch? What if they actually they de-wet and they actually touch? So we have sand-like friction. Lo and behold, you can get enormous viscosities then. And they did lots of simulations and they quantitatively compared against our data very favorably, but they needed a very large friction coefficient of 1, right? So that's very large friction. But they could get the response if they put that into the code. However, when they went and simulated the normal stresses, which they get out of the computer calculation at the same time, lo and behold, the values are either 0 or positive. And ours are negative. There's a negative sign in front of our data. So if you look at the whole rheological profile, the simulation of contact friction doesn't work here. So that spawned a lot of work then in our lab and others to go back and actually ask the question, can we measure this nanotribology, right? And can we then correlate that with the rheology by going through the structure? And that's what I want to show you next. So we worked with Lucio Ise's group at ETH Zurich. They did some beautiful work where they glued a particle to an atomic force microscope. And they added our particles to the system, and they rubbed our particles against each other in the fluid. And they came out with data that suggests the friction coefficient is super low. A value of 0.08 is really low friction. That's a very lubricated surface. Typical in biological systems, maybe the cartilage in your knee, right, if it's working properly, really low friction, which confirmed what we were seeing, right? We didn't see contact between the particles. We weren't getting that effect. But then if it's not contact friction, then what is it, right? What could it be? Why is the viscosity too low, right, when the simulations, with all the wonderful physics in them, can't predict this effect? Well, we partnered with Joao Maio's group at the time, Case Western, and a very talented student, Safa Jamali, who's now an assistant professor at Northeastern University. And we asked the simple question. He had his computer code that had all the hydrodynamics in it, but allowed us to essentially have deformable particles. And when you have a deformable particle, as you squeeze them together, you get a much bigger contact area for the fluid and much higher forces in between there. And lo and behold, there's a lot on this plot. Our data's there, their simulations are there. Pretty good, qualitatively reasonable. Even more importantly, the first and second normal stresses are negative in this case, okay? And what's plotted there is the negative of N1 and N2, okay? So it compares reasonably well. So qualitatively, this works. And the value of the softness of the particles that they had to use is consistent with our particles which have an organic coating on the surface. So it's promising. Safa went on, when he started at Northeastern, to work back with John Brady, who did the original Stokesian dynamics simulations, and asked the simple question, well, you know, if you have particles like ours, and you think about what's going on in this nanotribology, you have a contact region, and is there fluid in between, or do they actually touch, right? Well, what if there's fluid in between, and how do we model that? So they took their colloidal particles and they put little asperities, little particles on the surface, and then ran the computer calculations with all the fluid mechanics and calculated the rheology. So basically the particles never touch, they never de-wet, but they can't slide by each other so easily because of the roughness, okay? And if you put that in, lo and behold, you get beautiful shear thickening. And further, if you look at the details of the results, you get negative normal forces. So here we go. We can get the shear thickening, we can get the negative normal forces, and we can do it either by having the particles slightly deformable or slightly rough, but never touching. That's important for designing systems, whether they touch or not. It's actually important. We wanted to go deeper. We like neutrons. Neutrons are like light. So you're used to lasers and light scattering. We talked about Meyer Birnbaum's experiments using diffusing wave or dynamic quasi-elastic light scattering, as Heim said. We use neutrons in the same way. Neutrons are everywhere, right? We're made up of neutrons, right? But you get them out of a nuclear reactor. But the nice thing is they penetrate ceramics and metals and titanium, and you can look through materials. And so we're going to use neutron scattering. We're going to ask the question, are these cartoons realistic? These are cartoons. And simulations predict this, but what do we know for reality? So I had an extremely talented graduate student, Kate Gernon. She now is the rheologist for the General Electric company. I think you may have heard of this place, right? She runs down here in Niskayuna, runs the rheology lab for the company, which is kind of interesting. And anyway, so she said, okay, let's take some neutrons, which we get out of a nuclear reactor, and let's put them through our rotating cell in the rheometer, and let's look at the structure, and we need to do this in all three planes of flow. A lot of technical details, but beautiful results come out. So here's a typical flow curve, viscosity going down and back up again in the shear thickening. And this is what we see on the detector where we subtract equilibrium from the pattern. So we don't see much at low shear rates because we're near equilibrium. And as we go into the shear thickening regime, suddenly beautiful structures emerge in the suspension as measured with our neutrons. And I've blown up one here where red means we have more neutron scattering and blue means we have less. So it's a heat map. But that anisotropy and that change in structure can be related back to the stresses. Once we know the structure, we can multiply it by the hydrodynamic forces and other forces and calculate the stresses, and she did that beautifully. And sure enough, the kinds of structures that are in that cartoon are the structures that we measure here. It's very interesting. And then another student, Yufan Li, who's now in Europe doing his postdoc, but did beautiful work with Comores. We took those patterns and we looked at them in another way, sort of a polar plot, where the magnitude here tells us that intensity, so that we could compare more accurately against the simulations. Okay, so he was clever, and he said, I will make particles that de-wet. I will make particles that have a friction coefficient close to 1. And I'll compare them to the particles that have the low friction coefficient. So the coated silica, low friction, the particles with friction that we know for sure touch. The neutron scattering patterns are different in the shear thickened state. So the structure is different, which is what we were hoping to see, right? We could really distinguish with the structure the nanotribology. And again, the normal forces on the other side are positive, and one on the right are negative, right? So we see differences in rheology, we see differences in structure, and quantitatively you can compare these. So interestingly enough, with the neutron scattering, we could pick up the differences in the nanotribology. Finally, we tried to compare against the simulations. People simulate things. You can average stuff to get rheological properties as an ensemble average, but when you look at the details of the structure, you really need big simulations. So we looked at Safa's simulations with the enhanced lubrication. We looked at Jeff Morris's simulations. They gave us the data, and we compared. And here's a typical pattern. Our data is the green. The one theory is the red. The other is the silver. What you notice immediately is it's too noisy. The simulations are too noisy. When we do an experiment, we measure 10 to the 20-some particles. When they do a simulation, they measure a few hundred, maybe 1,000, right? So the statistics just aren't there. So the conclusion of the paper is we need better simulations, right, to be able to see the differences in the simulations. But we can see it in the rheology, and we can see it there. So quick conclusions for the first part of the talk, the next part short. We have these different theories for shear thickening. Different systems have different behavior. The rheology can distinguish what's going on in the nanoscale if you interpret it. The nanotribology, turns out I didn't go into that in some details, a little tricky, so it's not a one-to-one match between what you do in an AFM and what you see in a suspension. Neutron scattering, we can measure the differences and relate that back to the nanotribology, but also get a good idea on then how to modify systems if we want to control that shear thickening. Simulations aren't there yet, though. They need to do more work, these simulators in the room. We need larger systems in particular. But now we have a large data set of rheology, microstructure, and nanotribology, which people can use to test theories, right? Okay. I've always been dreaming of Mars. When I was at Carnegie Mellon and taking classes with Guy Berry and that, Carnegie Tech, and it was still a dream at that time with NASA, right? I'm old enough to have watched the Apollo landing, right, on a black and white television, right, in Pennsylvania. As a kid, it was very inspirational. Artemis mission, we'll find out at 3 o'clock today, apparently, what's going to happen with the launch, whether it happens next Tuesday or not, if the NASA engineers can solve the hydrogen leak. We want to go to Mars. Now, getting there is hard. Hollywood has shown us that, right? Sandra Bullock and Gravity, right? Micrometeorites. Well, guess what, right? There have been significant problems with this MMOD. NASA, you've got to have acronyms. MMOD, micrometeorite orbital debris. Very dangerous. That's not a cartoon. That's NASA tracking everything it can track. And you know they have to move the space station every now and then because some Russian satellite blows up and the pieces come by. We've heard of that. Well, it turns out to be also important. MMODs can also hit the space station and do damage. This is a railing. Astronauts, when they do spacewalks, tend to grab those railings. That sharp metal is because of a small piece of dust hitting that railing at incredibly high speeds, melting the aluminum, and it re-solidifies like a knife. And it cut the glove, and the astronaut had to cancel the spacewalk and come in. Because if you get a puncture in your spacesuit, you have about 3 minutes of reserve oxygen before you die. Got to get back inside, 3 minutes, right? So very serious issue. A spacewalk costs us about $1 million to put an astronaut up to do a spacewalk. So that's a pretty expensive problem. So of course, the other problem is once you get to the surface, right? Mark Watney, The Martian, right? Another Hollywood movie, you saw what he went through. The dust. The Apollo suits came back totally destroyed. The regolith is like volcanic rock. If you've ever been to a volcanic area, you know how sharp the rocks are. They cut up your hiking shoes, right? You don't want to touch them. They'll slice right through your hand. My wife actually has 8 stitches or 9 stitches in her hand right now because she slipped and fell and hit a piece of rock that was sharp, right? It's so easy to cut through, right? While hiking. So NASA's interested in spacesuits, and our company's working with NASA on that. And as we look at the Artemis mission and then ultimately the real goal, eventually getting to Mars, we not only have to worry about these MMODs and cut and puncture in space, but we're working on the surface of a planet. We've got dust. Astronauts will be in contact with sharp rocks and sharp objects, right? So let's go back to our armor. And here's a picture of a bullet in a Kevlar vest. If you blow up the Kevlar, it's a plain weave fabric. And you blow up a little more, you can see the shear thickening fluid inside impregnated. It's dry. You can pick it up. It feels like a normal fabric, but it's got the shear thickening fluid in it. If you blow it up now with electron microscopy, you can start to see the nanoparticles in between the Kevlar fibrils that make up the yarn. They're the particles. And if you're Hollywood, you pick up on this, and if you're a Daredevil fan, the Daredevil's suit is made of our armor. If you read episode 8, right, he explains how his suit is made. It's the recipe for our armor. Anyways, this is the outer portions of a spacesuit, what's called the thermal micrometeorite garment. It's to keep the heat in, keep the air in, and keep everything else out, right, puncture and dust. The outermost layer is called orthofabric. That's the white you see of the astronauts. The Russians have a different color, different fabric. Inside is eventually a bulletproof ripstop nylon that protects the bladder layer that keeps the air in. So we've been modifying both the orthofabric and the absorber layer, it's called, and modifying that. The spacesuits were designed in the 1950s and 60s based upon the technology that DuPont had. DuPont's at Delaware, we're right next door. Okay, so you get an idea there. So we've been working on this problem for a while with NASA. We do some very interesting experiments. Some of them are done at White Sands Missile Range in the test facility. What you saw here on the video was a little piece, a very small piece of dust, basically, hitting a piece of aluminum, which is used as shielding on like most spacecraft, and blowing up, right? And so the outer layer of the spacesuit has to do the same thing, has to disrupt and destroy projectiles so that the absorber layer further back can absorb what's left over and the energy of that, and keep the air in. A little bit of data, just to wrap up. One thing is, how much weight do we put in? Well, the orthofabric and the Spectra, when we treat it, it's about 30% heavier. That's important. Is it flexible? Well, remember, at low shear rates, the shear thickening fluid has a very low viscosity. So flexibility is not a problem under normal motion, okay? And its flexibility and its basic overall behavior is exactly the same as the normal fabric until you hit it. If you try to puncture it, all of a sudden, you see the Spectra layer, which is a replacement for the nylon that we're using, a more modern version of the ballistic materials, increases by factors of 2, right? 125% additional force. The outer layer, the orthofabric, which really isn't designed to be very resistant to puncture in that, goes up, factors of 3 or so. So it's a huge improvement with not a huge improvement of mass on the suit. What about this hypervelocity impact? So now we go to white sands and we have these tremendous guns that shoot small projectiles at 3 kilometers a second. So I could get back to Delaware in the time it takes me to finish the slide, right, at that speed, right? So incredible velocities. That's what you see at night, right, the meteorites you see. That's small pieces of dust burning up in the atmosphere. So the normal suit penetrates at around 3.5 kilometers a second. That's a piece of hardened steel, which is like a protective plate at the back. It's called a witness plate. And you can see the damage, the small piece of nylon, a couple millimeters of nylon did at that speed. Here's the STF-treated, shear thickening fluid, by the way, if you haven't caught on to the acronym yet, STF-treated fabric. Nothing got through, and in fact, the bladder layer is damaged, but it still holds pressure, right? It would not have penetrated through, the suit would not have leaked. Good news. So what have we been doing to wrap this up? Flight experiments, right? So NASA's been very good working with us to put things into space and see if they'll actually function outside, right? So we have the materials in International Space Station experiment, MISSY. We've been there from the beginning of this. We've got 4 experiments so far. And it's a lot of fun. So we get to work with astronauts. Here's Dr. Kate Rubins, who's just a phenomenal biochemist. If you ever want to meet an astronaut and talk to some of the most brilliant people you've ever met. That's Maria Kasarova, and Melissa Gordon, who was a PhD student at the time. Now she teaches at Lafayette College, and Maria works for Lubrizol Company, a lubrication company. That's actually in the Russell Building in the US Congress. This is Maria at Johnson Space Flight Center in Houston, working to put our materials together, of course, all clean room and everything to go on a flight experiment. And we were guests of SpaceX early on when they first started. SpaceX 14, one of our first missions, they took it up in the Dragon and put it there. It's a lot of fun. It was a very interesting first experiment to do. As much as neutrons are big science, NASA launching things off the planet's even bigger, right? Here's some data just to show you. So there's the carriage that's on the outside of the space station. There's a little arrow there that shows you where it is. There's our samples, different controls. One thing that happened is there was a little bit of discoloration right at the surface. This turns out to be ultraviolet. There's very harsh conditions. Atomic oxygen, ultraviolet. But the good news and the unexpected news is that the materials got better after a year in space. The puncture resistance got better, right? We don't fully understand why, but as the graphs show you, the box plots, they're noticeably better after a year in space. So there's something about aging materials in space that in this case worked in our favor. If you put normal Kevlar up and other plastics, they go to pieces in a year. So the STF really protected it. It's very interesting. So there's some conclusions about this work. I don't want to belabor it, but our materials are superior, right? And we're hoping to get them integrated. We're working with the contractor who's building the suit for the 3rd Artemis mission when they will go to the surface. We're hoping our materials are down selected for the final suits. We've been optimizing the material design. We've had a couple of experiments. The mission post-flight testing revealed unanticipated benefits to being in space for our materials, which we don't fully understand but are quite interesting. There's a lot of exposure to atomic oxygen, ultraviolet. The discoloration we know how to solve, and we're working on that right now. And in fact, our materials were selected for one of the first lunar missions. NASA will put things on the moon before astronauts and test them out, and so we've been now selected for that. I want to close by thanking some people. One, I want to mention some very talented undergraduates. One of the hallmarks at Delaware, not only do we have very good undergraduate students, and graduate students, we also have very good high school students. So here's a high school intern, Jacob Hughes, who worked on some of the second experiment we sent up with Erin Hogan, who graduated with an honors thesis. That was her honors thesis, to launch something off the planet. That's kind of a fun project for an undergrad. She now works with young adults in an NGO, trying to help them recover from COVID. She was mentored by another undergrad who worked with me, Elaine Stewart. Elaine came to Delaware as a NASA-funded intern. She has been one of the key engineers on the James Webb Space Telescope. She has followed that telescope all over the country and all the way to French Guiana, was there for the launch, and she's still working with the Nobel Prize people who are at NASA analyzing it and taking care of it. Very proud of her. I need to thank my research group. Special thanks to the Birnboim family for this opportunity to share with you some of the exciting things we've been working on. Some books you should read, okay, if you want to learn more. Some very talented people in my research group and some funding. Thank you so much for your, I'd be happy to answer the questions. So don't be bashful. Sure, Steve, go ahead. We'll start with students. So students always have the best questions.
Yeah, so the question from student?
Nothing's
Anyone?
off the table. You got to be curious.
No, really? So then, I mean, meanwhile, the students thinking about the good questions. So let me start to read this question. So the shear thickening is, based on my naive understanding, is shear thickening happens because when a certain part of the material is stressed, it's a ring scale that the force propagate, and the time scale also exponentially increases with that. But why it does not fail like a regular solid, like a biscuit?
Yeah.
So biscuit, it fails if we push hard.
So your question's a really good one, Sang-Woo. So let me just rephrase it a little bit. So part of it is like, if the shear thickening fluid works the way we're talking about, why doesn't it also fail under some conditions? And it does. So a little quick story. When we were doing the body armor work in the beginning, I got a call from the BBC. They said, we want to do an interview with you live on the BBC about your work. And I said, that's fine. And so he said, oh, how about 3 o'clock your time? And I said, that's fine. Call me in my office. Call me in my office. And the guy was all excited, but he had no knowledge of what we were doing, no real technical knowledge. And so he asked me this question. He said, can I use the shear thickening fluid like a sunscreen, slather it over my body, and jump out of an airplane and survive? Now, what he had seen were videos where people take a bag, fill it with that oobleck, put an egg inside, and toss it off the roof. And we've been guilty of doing that at Delaware too, right? And sure enough, the egg survives, right? Because that's shear thickening fluid. But it's because it's contained. And so the sunscreen doesn't work. The Kevlar, the fibers there, are the containment. The shear thickening fluid is inside a structure, right? So it does its thing. Like any material that isn't connected, like polymers have entanglements and connect, or textiles are woven, right? They connect. The particles aren't connected, so they can be pulled apart. So it will fail under tension, right? So you don't want to just use it as like a sunscreen. You need to put it in some kind of a containment system so when it shear thickens, it can lock up and hold the fabric together. So when the bullet hits or the stab threat hits the surface, you have locally high shear rates and stresses. The material becomes ceramic-like, and it can't penetrate through because you have a fabric there. So if you use a weak fabric, it will not work well for the ballistics in that. So that we need to use Kevlar, which is 10 times stronger than steel when you stretch it. So then when you stretch the Kevlar and our materials in there, it makes it like a ceramic with Kevlar nanocomposite, right? That's a great question.
Thank you very much.
There's a couple here. We got to go here first.
Sorry, George Beach. So Norm, wonderful and very inspiring lecture. So when you think now about what you know about shear thickening fluids and the various material science aspects, right? And you look back to where you were initially with the stuff, right? What have you learned, and is there still more to do to make it even better? Because optimization of materials is a very multifaceted optimization thing. Economics, this and that, right? Yep. How are your systems now different than what they were initially, and where do you think they could go?
This is a great question, Steve. So, the question is like, okay, what have I learned along the way? And I'm going to turn that a little bit, and then where are we going? I'm going to turn that around and tell you a story that I think is valuable for graduate students and faculty. So I was a young professor, and my first graduate student, John Bender, came from industry and worked at Air Products for 4 years. he was more mature than me in many ways. He had kids and a family and a wife that was working. And John was very driven, great student. And one day we were in the lab, we were doing optical rheometry, which is exactly what Meyer Birnboim taught us how to do, right? In that work with Guy Berry and that, and then later on in his career, using optical rheometry to look at the structure with lasers and light scattering. And one day he came to my office, he showed me beautiful data, and we went in the lab and looked at it and did the experiments again. And he said, look at the shear thickening behavior. And I said, no, John, no one wants shear thickening. We all try to avoid shear thickening. I said, you don't want to work on that for your thesis. He ignored me and did beautiful work. We published papers that I thought, well, maybe people care about this. Suddenly, the people doing simulations in theory who cared about this jumped up and down and said, you have data. You know what's going on inside this suspension, right? We had worked hard to make an optically clear suspension. So what I learned is trust your students. And don't underestimate their enthusiasm when they see something in the lab, and then, but make sure you go check it too, right? Make sure it's real. But we had fun. So where are we now? Well, it's interesting, right? The NASA project took us into low volatile lubricants, right? There's a fluid in there. You may have been wondering, how does this work? Doesn't it well, no, there are lubricants that work in space. They're very expensive. They're very difficult to chemistry, and so you have to engineer the system at a molecular level. So you're doing molecular thermodynamics and chemistry to get the physics you want by engineering the system. So the NASA work really opened up a whole new avenue of materials science because of the extreme environments. And it's been fantastic, right, working with the NASA engineers and the students and traveling around and doing things, because it puts us in a different world, right? And that. So I would say the intellectual challenge and the materials challenge really came when we started moving away from materials that would be in contact with humans. So when you have body armor and that, police, they're wearing it under the uniform. So the materials you use cannot be toxic in that way. And you certainly don't want, if a bullet gets through the body armor, you don't want to contaminate a wound with something that would be problematic, right? So these are all concerns, right? That when you engineer something for human use, you have to be very careful about. But then NASA took us to a whole new realm of materials challenges, which we're continuing to struggle with, but making some very good progress on. So thanks for that question. That's great. George, yeah.
So I have a comment first, and the comment is, who says being an academic is not a hell of a lot of fun? And I think that's a message you are giving all of us. If you can find a field that is relevant, and maybe one that goes into space, you can really have a fantastic life. You can go to all these places, you can meet all these. So I want to congratulate you on that. I think you've done wonderfully, and it's all built on Birnboim's original theory.
Absolutely.
So we have to thank
Absolutely, we must thank, yeah.
So now my question is, it's actually a question about those aggregates that are formed in between two particles, and your very nice pictures you showed with neutron scattering. And so the question is, can you influence the aggregation process by changing the chemistry of the fluid? Can you add salts? Can you add ionic solutions? Can you change it and see those changes, maybe enhance it and maybe not? Because I mean, my field is surface chemistry. I'm interested in changing surfaces. And I think you could do that. And I'm just asking if you could comment on that.
That's a great question. So the question after the very nice comment, in science could be fun. And engineering can be fun too, by the way. So one of the things I learned about starting a company is that when you really have to engineer, it's one thing to get it to work in your lab, it's another thing to make it work in the real world, right? And that's where partnering, like with Reebok, I mean, that was a really interesting experience, because they came from Boston, descended upon us at Delaware, and said, we have an idea, and you have a material, let's make this work. What was also interesting is that everyone in that organization who worked on that project were women. From the business people to the engineers to the scientists, and they had a passion for women's sports apparel. They said, we're tired of men's stuff being made for women, right? And we're gonna make stuff for women, right? So that was a great experience and a fantastic opportunity to work with them. Now back to your surface chemistry question, absolutely. So one of the goals, especially in controlling that shear thickening, the paints and the photographic process and that, is you might not be able to stop the shear thickening, but if you can move the onset of the phenomena outside of the regime of processing. So you squeeze toothpaste, you can only squeeze so hard. So as long as it doesn't shear thicken when you're trying to squeeze it out of a normal toothpaste tube, you're okay, right? The formulation's okay. But if you pick the toothpaste up off the shelf 10 years later, you might not be able to get it out anymore, okay? Because it's probably shear thickening on you because it's aged. So the surface chemistry you can use to often, you may not be able to prevent it, but you can move the onset around. Either move it earlier or move it later, because you're basically asking questions about, can I control how the particles want to move relative to each other? And do they want to stay apart or do they want to come together? And we found with some of the formulations, if we made them attractive, we could get tremendous shear thickening earlier on, because the particles already want to form the clusters, and then the fluid mechanics effect and that work together. And if you put a high charge on the particles, controlling the salt and the pH, change the charge on the surface, you could keep them apart. They're repelling each other, and you could keep them from wanting to cluster together. And so that's a great way to formulate a system to move it outside the range. We use that in proteins and biopharma too, where clusters form, maybe for slightly different reasons, but the same, and you do too. So the control of the surface chemistry is the fidelity of that gives you a handle, right? And I showed you that one slide where we checked all the particle size, polydispersity, all the, we just systematically went through, right? Just experimentally testing all of these ideas. And then you could relate them back to simple colloid science theories about the forces and make some argument about which force was bigger. So you can do a quantitative analysis or semi-quantitative analysis using colloid and polymer science tools and simple theory to tell you how the particles are interacting and compare that to the force of the fluid. So that's what we do. Sure. Fine. Oh, question from student first, and then we'll get yours. Okay.
Thank you for your talk. Like my question is, can this material be used in transparent kind of applications, like in Indy cars or Formula One, or where, at the top of the towers or high landscape building, we have wind and particles which hit the glass and the glass might break. Can we use these materials in that application?
This is a great idea. So the question is, could we make essentially transparent versions of the materials? So there's good and bad news. The good news is the formulations, as I showed you, are transparent, all right? They can be made transparent. The nanoparticles and the fluid can be matched in refractive index. The problem is the containing material. So you need it then to match the rest of the material to be transparent. And so it's close to glass. So we have started working with NASA on a composite structure where we're using traditional composite technology like reinforced glass, S-glass, or carbon fiber that you all heard about. And we're using layers in the composite layup, which composites are made of many layers, which include our technology in there, so that when there's an impact, like you're in a car accident, or you're an astronaut, and the hard part of your suit, which is composite, you fall over and it cracks, right? That's not good. To prevent that damage, and it works really well. We can really make composite materials that are incredibly damage resistant and still very strong, and that's work we did with NASA. And now we're trying to propagate it down into automotive and aircraft. They're not transparent because not our formulation isn't transparent, but the composite material is opaque, right? Because of the carbon fibers and things. So if we could work with a material, that's a great challenge, right? Maybe you want to take up that challenge, right? To say, can I use the theory of optical, right, transmission of light through optical material? Can I engineer the rest of the material to have the same refractive index so it's optically clear? So that's a good idea. We haven't done it, but we can make composites that are incredibly tough. And we're actually showcasing some of those at a composite show this fall, the CAMX show, those of you in the composite area, but they're a NASA spinoff, right? Yes.
Yeah. First, thank you for this talk. It was really wonderful, and different levels of science in our group. I'm sure we all enjoyed it at different levels. I had a question which may be too complex to deal with in the time here, but when I was listening to this, and actually this is a new area for me, I was more familiar with thixotropic materials.
Ah, yes.
And I wondered, which is exactly the opposite.
Yes.
So is there an easy answer why they're the opposite?
That's a great question. So Haim's question is about thixotropy, which is Greek, but essentially what it's saying is that you start with a material that essentially is solid-like, and as you shear it, it becomes more fluid-like and flows, and then it becomes more solid-like as you let it rest and goes back. So you can make these materials thixotropic. That's a great question. You can make these materials thixotropic. And there's some reasons why you would like to do that. So for example, if you want to make a gel, make a shear thickening fluid that's also a gel. Let's go back to throwing the egg off the roof, which college students seem to like this experiment. I don't know why. We could do watermelons too, but then you need a lot of material. You really want a gel material. So a colleague of mine, a former postdoc worked at Delaware, Srini Raghavan, has published some very nice work that's gotten a lot of attention. He's at the University of Maryland on the faculty there, where he added some interesting polymer structure, a hydrogel, and put our shear thickening material inside the hydrogel to get a thixotropic material. And then he was throwing eggs off the roof, but in a more scientific way, and showing it really would work well. So the idea was you'd have a material that's more like a putty or a gel, right? But then when you squeeze it hard, it shear thickens. So you get both effects. So in a way, you can engineer it to have both effects. Often you need to add something else, maybe changing the surface chemistry or adding a polymer like Professor Raghavan did. But that's a great question, and thixotropy is something we love and hate, right? It's a difficult thing in material processing because it's a time-dependent rheological properties. And luckily for us, the shear thickening happens so quickly in these nanoparticle systems that there isn't much of that time dependence, so the effect is fast. I mean, I showed you the bullets and the super fast micrometeorites. The first question we had when we did that experiment was, would it go through faster than the material could shear thicken? And so we did a series of tests at the University of Delaware where we had what's called a split, the physics people will know this in materials, a split Hopkinson pressure bar, where you essentially shoot two bars together and you smash a material in between and you measure what happens. And we did the experiments there. Very talented young lady, Amanda Lim, who then went on to work at Livermore Labs. She did those heroic experiments and analyzed them and said, look, it shear thickens, right? Even though we're smashing these bars together at incredible velocities. And then we went to White Sands and did the measurements, and sure enough, it worked inside the fabric, right, as well. So it was a question, though, would it happen fast enough, right? And then later on, people did some theory and said, yep, it's fast enough, right, for the micrometeorites. That was cool. Thank you for that question. There's one back there, yes.
Hi. Hi, thank you for your talk. It was very interesting. I had a question pertaining to when you said these materials that you were testing were completely reversible with their shear thickening behavior. Has there ever been circumstances where you find that it's not irreversible? Like, say if you have it under like a compressive load for an extended amount of time. I'm thinking something akin to like a strain hardening.
Yes. Okay. Great question. So as I showed you, to rephrase the question briefly, I showed you the material was, and I claim was reversible. And that was partly because the fluid is always there. So think about the bearings in your car, right? They last a very long time because the metal parts never touch. And if the grease leaks out, the metal touches, you're done, right? You go to the garage, get towed, right? So same thing here. If you can get the particles to de-wet and touch, then they will grind against each other and you will create damage. And then the next time you try to shear thicken, you'll get more damage. And we've done those experiments. So you can push these particles that I showed you to very high stresses. And if you repeatedly push them to very, very high stresses, they will start to damage. You'll get surface damage. And then you'll start to grind, right? And then once that happens, things go bad pretty quickly, just like you would imagine in a bearing in a car. Once you get a little bit of dirt or damage, then that's why you change the oil in your engine, right? Because the little metal particles in that, if you don't get them out of there, they start to do more damage. It's autocatalytic, so to speak. You get more and more damage. So the same is true here. And that's why it was important for us that we didn't have Edmondson's law of contact friction in our system if we wanted to use it in these applications. Because you can imagine, you know, you're an astronaut, you're moving around for a month on the surface of Mars. You don't want your suit to degrade itself, right? Because the particles start to grind against each other. So the fact that it's reversible at those stresses and doesn't cause any trouble is really valuable, right? If the particles were touching, like sand, they would rub against each other and that would create damage and then the material would fail, right, catastrophically. So the answer is yes, you can engineer systems that will do that. No, you probably don't want them if you want the material to be anything other than a single-use material, right? Okay. Thank you for that.
Okay. Any other question?
Sure. We got one here. Yes.
Thank you. Oh, it's a very, very cool talk. I was wondering, how do you get the fluid to not transfer or leach out of the fabrics?
That's a great question. How do we keep the fluid in the fabric? So, you know, the Army and those applications, they need to last 10, 15 years, right? In a hot trunk and that. So we've had body armor hung up at the Army lab doing all sorts of things over the years, and it doesn't leak out. So the first question you might ask is, but if it's shear thick, is how do you get it in, right? That's the first question. And then the second question is, once it's in, why doesn't it just come out? Well, the second part's the easier one because of surface tension. So the kind of surface forces that we heard about, right? If we tailor that right, the capillary forces holding the, because we're talking nanoscale, right? Those particles are nanoscale, right? The distance between the fibrils is on the nanoscale, hundreds of nanometers. So then capillary forces are dominant. So that's enough to keep everything in against tremendous forces. But how do we get it in the first place, right? So what you do is you dilute it with a carrier fluid and then you dry it back out, right? So the fabric is when you make the fabric and then you push it through a bath, right? You squeeze out all the excess off and out of this. You get the amount you want by squeezing it out, and then you dry it. So in the end, you're left with the particles and the fluid are contained between the fibrils that make up the yarn, right? But they're not on the outside. It's not like a coating on the outside. It's fundamentally inside, and then the capillary forces hold it in place. We've had body armor hanging, it's almost 15 years now, right? And we measure what's going on. And, you know, no drainage, no leakage, right? Because the capillary forces are just so strong. The gravity force is very weak on the nanoparticle.
Follow-up question, can they be washed?
Yes, and that was an important question. So the astronauts, how are we going to clean off the suit on the outside? Maybe not with water, but air, maybe, or maybe water if we had to, right? Because that, by the way, that dust, the Martian regolith, is poisonous. If you bring it inside and breathe the atmosphere, you will die eventually. It will be poisonous. That has things that outgas from it in a normal atmosphere. That's sort of an interesting finding. It's not going to be so easy living on Mars. Got to clean that dust off, can't drag it back in. Can the body armor be washed? Well, people don't wash on purpose. The Kevlar itself, the base fiber, should never get wet. So in a way, we're actually protecting the fibers with our material, and then it's usually encased in a breathable but waterproof, like Gore-Tex type material, so that some water vapor will transfer through, but water itself won't get in. The sports bras are washable many times. Now, please don't use super aggressive Tide, right? I mean, the instructions are to use a more delicate detergent like you would for any sports apparel, right? But the point is, they're perfect, right? But that required some engineering of materials that could withstand, and this is working with Reebok, this is the kind of real-world situation. If you make athletic apparel, then it needs to be washable, right? So we had to formulate one that could handle normal washing, right, with a reasonable detergent, right, to stay clean. So it can be done. It can be done. These are great questions, and they're the real world. When you're confronted with the real world, you get some really interesting science questions you have to work on because you have to reformulate new materials, right? So, yeah.
Thank you.
Thank you.
Okay, everybody, let's thank Professor Wagner for a really fabulous seminar.
Thank you. But we have to thank the families, yeah.
Let's also thank the Birnboim family for establishing a new tradition here at Rensselaer.
Thank you so much. Thank you very much.